Okay, students. Hi, welcome to the lecture on thermophysics for Olympiad training. I'm Mr. J, and I'm doing I suppose, the least fun topic in the whole of physics, thermodynamics. Thermodynamics deals with a statistical treatment of a large number of objects, as opposed to mechanics, where we usually looked at one or two or three individual objects and their forces on each other. In thermophysics, we like to treat multiple identical uh, objects, such as gas particles or liquid particles or solid particles, as a large bulk arrangement of matter. So there are several physics laws that still govern our thermophysics equations, and of course the principles that apply to our individual small particles also should apply on the large scale. So for example, what we're going to learn in the first half an hour will be on the first law of thermodynamics, and the first law of thermodynamics is actually a reformation of conservation of energy for a gas system. So without further ado, let's take a look at what we are starting with. So we're going to start with thermophysics, first law of thermodynamics, and straight off the bat, the first law states that the change in internal energy of a gas system, or of any system, is equal to Q, the heat supplied to the system, plus W, the work done on the system. So based on certain restrictions, okay, we can have certain consequences, and that would simplify this equation for us to get some useful results. So without explaining too much, as Olympiad students, you guys will need to do quite a lot of self-reading. So I'm not going to be able to unpack everything within the first hour. Thermophysics itself is one entire course in university, and we're going to be covering quite a lot. So for the first half hour, we're going to cover the first law of thermodynamics. We're also going to cover specific molar heat, and lastly, we'll talk about energies of different gas molecule systems. Alright, so 3 different topics to cover in half an hour. I'll try my best. I'll not be able to go through all the worked examples, but I will send you this set of slides together as an attachment so you can see the worked examples. I think there are over 50 questions printed in the lecture notes. Those will be your tutorial questions for this topic. Not say tutorial questions, but rather your practice questions. So do try them. Some of them are worked examples, and the rest of them are for your self-practice. We'll go through all of this we won't be able to go through this. I'll send you all the solutions 1 week after this lecture. Alright, so let's get started. We're going to go through 5 different cases, and they have different volumes. You might have heard of them. We will definitely be doing this again in H2 physics because it's important, but probably not in so much detail. So before we get started, we need to take a look at the symbols U, Q, and W. U is actually the change in internal energy. In this case, specifically for first law, it refers to an increase in internal energy. Internal energy is actually the sum of kinetic and potential energies of the molecules at a microscopic level. So for example, if you have a gas system, U, okay, refers to the sum of the molecular kinetic energy of all the individual particles plus the sum of all the molecular potential energy between all the particles added up together. So of course, if the mass of a gas is larger, U itself will be larger. So what we're saying in the first law is that any change to this internal energy of the system, which is thought as Ke and Pe of the molecules, must come in the form of either Q, supplying heat to the system, or W, doing work on the system. So the first case we'll look at is something called an adiabatic process. An adiabatic process is one where there is no transfer of heat into the system, and the system could be a gas. So right over here on the right, you can take a look at this picture. It shows us a canister of gas which is well insulated from the surroundings. That's why heat cannot be transferred to the surroundings. And we're going to put a heavy object on top of this lid here. So this acts like a piston, and this heavy object is going to rapidly compress the gas inside. But because the gas is compressing rapidly, and the presence of the insulation prevents heat exchange with the external environment, we're going to say that the process occurs rapidly and is well insulated. So putting Q equals to 0, where heat cannot be given to the system or lost from the system, into first law, gives us a simplified result, delta U equals to W, where delta U is the increase in internal energy of the system, is equal to the work done on the system by this lead shots. So this lead shot is actually compressing the gas, and that's doing work on the gas. That work is energy transferred to the gas, and is stored as the internal molecular kinetic and potential energy of the molecules, right? So energy is still being transferred to the system, and this is through work, which basically says that heat is not a valid way of transferring energy to and from the system. So this is called an adiabatic process. Second process we'll look at is a process which involves constant volume, also known as isovolumetric. So if the volume of a system, say a gas, is held constant, then that system can't do any work, because if the volume is held constant, you can neither compress nor expand the gas. You can't do any work. So in first law, what we will say is the work done will be equal to 0, which gives us delta U equals to Q. So for a constant volume process, we can still input heat into the system or take out heat from the system. And if I try to input heat into the system, it will be stored as the internal energy of the gas. Or if I try to take out heat from the system, it will result in a loss of internal energy from the gas. So actually it's a system where only heat is involved as a medium of exchange of energy from and to the system, from the environment. Third case, a cyclical process. A cyclical process is one which returns to its initial state. Now, when we talk about state of a system, actually what we are referring to is its pressure volume values. So if its pressure and volume return back to its original state or value after a series of changes, regardless of the process of the change, as long as it returns back to its initial pressure and volume values, we say that nothing in the system changes, including its internal energy, right? So its internal energy doesn't change. Its internal energy depends only on its current state. If you're not sure why, you can take a look at the ideal gas equation to check that. Indeed, if pressure and volume remain the same, exactly at the same values, then the temperature should also remain the same. So the amount of vibration of the molecules should remain the same. Therefore, its kinetic energy remains the same. So we say that in such a cyclical process, okay, delta U equals to 0. The internal energy of the gas neither increases nor decreases in such a process. And what this actually means is that if we look at delta U equal to 0 and substitute it into our equation, we get Q equals to minus W, right? Basically, it means that any heat supplied to the system must be lost as work done by the system, or any work done onto the system will be lost as heat that the system will lose to the environment. So as a result, the system itself of the gas acts as a medium of exchange for work and heat, right? So if you are doing work on the system, it loses heat. If your work is done by the system, it has to gain some heat in that process. Okay, so we call that a cyclical process. I'll show it to you on some graphs later on as we go through this lecture. Case 4. Case 4 is a free expansion. Now, free expansion is a special case where a gas is allowed to expand into a chamber which has no pressure. By no pressure, I mean that it's a vacuum. So if we consider this setup on the right here, we have two chambers, one with gas that's well insulated, and another chamber on the right which is also well insulated but has no air molecules in it or any gas molecules in it. Therefore, it is a perfect vacuum. Now, this stopcock here can be removed, and when that happens, the pressure difference between the two chambers will have to even out, resulting in some gas moving from the left chamber to the right chamber. This is called a free expansion. Now, in a free expansion, we are assuming that the system itself is well insulated. We're just doubling the volume or increasing the possible volume. So there is no transfer of heat to and from the environment external to the chamber. So we're considering this empty chamber here as part of our system. However, even though the volume of the gas now is apparently doubled, earlier on we said that, when there's no volume change, no work can be done on the gas, right? In this case, because the volume changes into a vacuum, no work has to be done by the gas to push its way into a vacuum, right? So we also say that there is no work done on the system. So in such a case, right, for a free expansion, the internal energy change is also zero, just like our cyclical process. But in this case, it's a one-way process that's irreversible, right? So in this case, since the internal energy doesn't change, the temperatures don't change, and P times V will remain constant. But the P and V, the values will definitely change. So it's not considered a cyclical process, because in a cyclical process, the P value goes back to the original value, and the V value goes back to the original value. In this case, because the volume has doubled, we definitely have a doubling of the volume here. But the product P times V will remain the same, which means that in this case, the pressure is halved, which makes sense now because the same container of gas now only has half of the number of molecules. So the rate at which molecules collide with the surrounding walls should be halved because there are half the number of molecules remaining, which gives us half the pressure acting on this container. So that makes sense, right? So this is a free expansion. Of course, we don't have to expand into a chamber with exactly the same volume. We could expand into a chamber with a larger or smaller volume, but the same result holds, that there won't be any transfer of heat because we are talking about an insulated environment, as well as there won't be any work done to expand into a vacuum. Okay, now this process is one that is very, very fast. It cannot be done slowly and in a controlled manner. So we call this an explosion of some sort. At any time, there will be a sudden explosion, and the gas will not be in thermal equilibrium, which means its temperature can change, right? And the pressure within the gas, of course, is not uniform as it's moving to the other chamber, but the final state will return it back into thermal equilibrium, and the pressure will go back to its original, will go to its new value and uniformize itself on the left and right chambers. So in this case, right, we can't actually plot the change on the PV diagram because we don't really know how the change happens. It's very sudden. Okay, it's not a gradual change. So therefore, we can't plot the expansion, but we do know the initial and final states. Alright, last case we'll look at is something called an isobaric process. In an isobaric process, the gas is kept at constant pressure. So if we are at constant pressure, then we know that the amount of work done on a gas is just P delta V, right? That's because the work done, okay, is the integral of P dV. So if the pressure is constant, we can take it out of the integral, and then it just becomes the integral of dV, which basically means inserting the limits of the initial volume to the final volume, the work done is actually equal to the pressure times the change in volume. So the work done is pressure times delta V, which makes our work done expression much simpler than before, which is normally an integral if our pressure is not held constant. Okay, so here are some worked examples for the first question. So I'll go through the question quite quickly. The first question, give me a second to pull up my copy of the questions. In the first question, we got 1 kilogram of water at 100 degrees converted to steam at 100 degrees by boiling, and we're keeping it at a standard atmospheric pressure. So if we're keeping it at a standard atmospheric pressure, the first question, part A, is how much work is done by the system during this process. The amount of work done, since the pressure is kept constant, will be W equals to P delta V. So we can actually calculate that to be 169 kilojoules. Next part of the question, how much energy is transferred as heat during this process? Now the process we're talking about is converting 1 kilogram of water at 100 degrees to a kilogram of steam at 100 degrees. So we're only talking about phase change. We don't have to heat the water up to 100 degrees. It's already at 100 degrees. So we will remember our secondary school equation, Q equals to mL, where L is the latent heat of vaporization. So given that the latent heat of vaporization is 2256 kilojoules per kg, the amount of heat supplied will be 2256 kilojoules. Last question, what is the change in the system's internal energy during the said process? So the change in internal energy can be found using first law of thermodynamics. Delta U equals to Q plus W, where W is the work done on the system. So since the gas is expanding, it is work done by the gas. So it becomes minus W by, right? So W on plus W on is minus W by, and this gives us 2.09 megajoules. So basically, in this process, although some work is done by the gas, by the liquid to become gas, all right, taking up a bigger volume, some energy is actually stored by the system as internal energy, and that internal energy will be in the form of the increased potential energy stored by the molecules, right? So in this case, right, there will be about 75% of the energy that goes into the gas, into the liquid. As it converts into the gas, it needs to increase its volume, and 75% of that energy goes to pushing back the atmosphere away. So this of course wouldn't be true if the expansion was into a vacuum. That means if I had a liquid water and then I heated it and made it into steam in a vacuum chamber, this answer wouldn't be the same because there wouldn't be that much any work done at all. So in this case, 75% of the heat goes into pushing back the atmosphere, and the rest goes into the system's internal energy, which refers to the potential energy stored by the particles. So here's a thinking question for you. Why is there no increase in kinetic energy stored by the particles? Alright, so there are a couple of there are many examples that in this set of slides here. So I won't be able to go through all of them. I've already used up 20 minutes to go through some basic processes. So please do read these yourself when you do have time. If you have any questions, you can email me. Alright, so I would like to talk about certain special cases next. So we're going to look at graphs of PV. Just now I said something about a PV diagram. This is a PV diagram. A PV diagram is a graph with pressure on the y-axis and volume on the x-axis. Alright, and if you can see, this coordinate P times V actually parameterizes a third variable, T, which is the temperature of the gas, right? So if you know the P times V value of a gas, you actually also know its temperature, because from the ideal gas equation, PV equals to nRT, something you probably would have learned before. And of course, we're talking about ideal gas at this stage, from this stage onwards, alright? If we do talk about real gases, I will specifically mention that, but otherwise we're talking about ideal gases. So here we have a plot of several changes. So a change basically involves it could be compression or expansion. So in a compression, of course, volume goes down. In an expansion, volume goes up. When it's compression, work is done on the gas. When it's expansion, work is done by the gas. So in an isothermal process, okay, an isothermal process is another special case. We are keeping the temperature constant. Now, if we're taking the temperature constant according to the ideal gas equation, the product of P times V must remain constant as well. So if we have an isothermal process, it must follow along one of these curves, where each curve is representative of a different temperature. We call such curves isotherms, because all points on such a graph have the same temperature using the ideal gas equation. So all of these points along the curve have the same product of P times V, even though the P and V values themselves may change, as I'm doing, say, an expansion along this isotherm, or of a different isotherm. So of course, if my system is held at a different constant temperature, it would travel along the different isotherms. Okay. So let's go through the work done by an ideal gas during an isothermal expansion. Now recall that work done is integrate P dV, right? But of course, now that the P is not constant, we cannot just take it out of the integration. But we do know from our ideal gas equation that P is nRT over V. Right? And nRT, N is the number of moles, R is the gas constant, and T is the temperature, which we are keeping constant in this question. We can pull it out of the integral sign. So we're actually integrating 1 over V dV. And we do know how to integrate 1 over V. It gives us ln V. So once we do the integration and put the limits in, we'll get to this result for the work done. the work done on a gas during an isothermal expansion is nRT ln Vf over Vi. Of course, if the final volume is actually smaller than the initial volume, we know that this value here will be negative because the ln will be a number that is smaller than 1. If it's smaller than 1, ln is negative, and this makes sense because if I have a smaller volume at the end, it means that I have a contraction. And if I have a contraction, this means that work is done on an ideal gas. Alright, so that's all. Right, so this is a summary of what we just discussed. In an expansion, the ratio of Vf over Vi is more than 1. So the ln is positive. This gives us a positive work done by the gas. So if you get a negative work done by the gas, this means that actually the gas was the one that did work. So it is work done, work done by ideal gas. Okay, so this is the work done by an ideal gas if it's positive, sorry. So if it's negative, then it's the work done on an ideal gas because that's a contract. This is a compression, right? So when the gas is expanding, the gas does work. When the gas is being compressed, the work is done on the gas. And work is done on and work done by is related by a negative sign, that's all. Okay. So I think this one is very straightforward. I think you can try the problems yourself. So here's 2 examples that actually use this concept. So do try these questions at your free time. Alright. Okay, not bad. We are already exceeding in time, but it's okay. We will attempt to do as much as we can. So after we're done with discussing all these standard processes, isobaric, isochoric, isothermal, adiabatic, and free expansion, we can talk about specific molar heats. So in secondary school, you have learned specific heat capacity, right? So in this case, we are talking about, instead of per unit mass, we're talking about per unit mole. And it's convenient for us because in the ideal gas equation, right, there's n, the number of moles. So let's see how it figures into what we have already learned so far. So for a monoatomic ideal gas, the value of U itself, not delta U, is a sum of what we call the molecular potential energies and the molecular kinetic energies. Just that for an ideal gas, it doesn't contain any intermolecular forces, so therefore it won't have any potential energy. So the only form of internal energy it can contain is about the kinetic energy of the atoms or the molecules that comprise the ideal gas. So if we have a single atom, it can be shown that the kinetic energy on average is 3/2 kT. Alright? This is for one atom. So if you want to get n atoms, it will be 3/2 capital NKT. If you want to get 1 mole of atoms, you have to do your own calculations for using Avogadro's constant, but I think you get the idea. Now, you can Google YouTube on how to derive the average translational kinetic energy of an atom. Okay, and actually we'll cover it later on in H2 physics as well. Alright. So I will leave you all to read if we're not at the work examples yet, no problem. Let's take a look. Alright, so let's consider a sample of n moles of gas. Within n moles of gas, each mole has Avogadro number of atoms, right? So the total number of atoms contained in n moles of a gas is n times Avogadro's number, n times Na. Alright, now we know that the internal energy of a gas is the sum of all the kinetic energies of all the molecules in the atom. And since it's an ideal gas, this is just the sum of all the kinetic energy of each atom, right? So each atom contains 3/2 kT of kinetic energy. So the total internal energy stored by the whole gas will be n times Na times 3/2 kT. Now if you do a bit of quick math, we are able to convert this K, which is the Boltzmann constant. Boltzmann constant times the Avogadro's number gives us the gas constant R. Alright, the internal energy of a monoatomic gas then can be seen from this relationship. The internal energy, not the change in internal energy, but the absolute value of the internal energy, is related to 3 constants: 3/2 factor, number of moles, and the gas constant. These are all constant for a gas that is not changing in the number of molecules, times T, which is the temperature of a gas. which means that for an ideal gas, right, the internal energy depends only on its temperature, something we mentioned a bit earlier, right? So that is the relationship between internal energy and the temperature for a gas. Alright, some worked example here that you all can go through yourself. Okay, so let's start talking about this specific molar specific heat at constant volume. So let's say we have an ensemble of n molecules of monoatomic ideal gas, and it's in a container where the volume is fixed, right? So we want to add in a certain amount of energy to heat up the gas. So let's call the amount of energy we add in as heat Q, and this will cause the gas to have a rise in temperature. Now, because the volume of the gas is fixed, the gas doesn't expand, so the gas doesn't do work, right? So this means that actually the gas would increase in its internal energy. Right. We have learned heat capacity before in secondary school. So now we're going to write an equation that relates the amount of heat transferred to the gas times the temperature change with a constant value that it relates these two together. So we can get the equation. Remember, Q equals to mc delta theta for specific heat capacity. Now we're doing specific molar heat capacity. So Q, the heat supplied to the gas, is nc delta T, where this C is called CV. CV is the molar specific heat at constant volume. Now it's important that we do this at constant volume, because when we then plug it into first law of thermodynamics, right? For first law of thermodynamics, delta U equals to Q plus W. So since volume is held constant, W is actually 0, delta U simply becomes this simple equation. We can rearrange and put the gas constant, right? Sorry, what do we call this again? Molar specific heat on the left hand side, and everything on the right hand side will nicely add up and cancel off itself to leave us with 3 over 2R. So it turns out that this constant, we recall that specific heat capacity is different for different solids, right? For monoatomic ideal gases, right, it's a specific value of 12.5 joules per Kelvin per mole. Okay, so all monoatomic ideal gases have the same molar specific heat at constant volumes. Okay, we have done this for constant volume. Let's see how it's different for constant pressure. So you can expect that we are going to calculate this constant called Cp now, right? So same thing, we're going to consider a system of n moles of monoatomic gas, right? And we're going to supply heat Q to it. And this will cause the temperature to rise by a small amount T to T plus delta T, right? So we're going to write down an equation that looks like heat capacity again. So Q equals to NC delta T, where the C now is called molar specific heat at constant pressure. Now we insert this again back into first law of thermodynamics, but now we can't let the work done be 0 because we are doing this at constant pressure, which means the gas is allowed to expand or contract. So since we're heating up the gas, we expect that the gas expands, right? Because when the gas gets energy, it tends to expand, right, as we heat it. So some of that internal energy, some of that energy that we give it from heating will be stored as internal energy. Basically, when the temperature increases, the molecules vibrate faster, thereby increasing the internal energy. But some of it is lost as work done by the gas. So we know that work done by the gas is actually the negative of work done on the gas. So the W becomes a minus W, where W refers to the work done on the gas. Work done by the gas. That's confusing. Alright, we know that the work done by a gas is P delta V. Right, where delta V is a positive number, which is the expansion of the gas, change in volume of the gas. Now, we know that from the first earlier case for molar heat at constant volume, the change in internal energy is related to CV. So we can put that back here on the left hand side. So we get a relationship between CV and CP. Right? So CP is actually CV plus R, and we know CV is 3 over 2R. So therefore, CP, the molar specific heat at constant pressure, is exactly 5 over 2R for monoatomic gases. Alright, so it's larger. Okay, why is it larger? Because some of the energy that you give to heat up the gas also needs to be lost as work done by the gas in order to expand, since we are not keeping the volume constant. we're keeping the pressure constant. Of course, if neither the pressure nor the volume is constant, this gets really complicated, right? So that's why we're considering this simple case of constant volume and constant pressure.